Hello, I'm Mr. McBrien. This is SPH3U, an introduction to waves. Ontario physics students will be able to distinguish between longitudinal and transverse waves in different media and provide examples of both types of waves. Students should be able to use appropriate terminology relating to mechanical waves and sound. Today we're going to define transverse and longitudinal waves and cite some examples of each. And we're going to learn how to describe the characteristics of waves. So what's a wave? Well, as good a definition as any is a disturbance which carries energy from one location to another. And we can talk about any kind of disturbance like this needs to travel through something. So we talk about the medium through which the wave travels. And the movement of this disturbance is referred to as a propagation. Okay, so there's two kinds of waves, and a longitudinal wave is one that we don't often think about. It's a wave in which the particles of the medium move in a direction parallel to the direction of propagation. And we can see an example here. And so what we get is essentially a pulse that moves through our medium. Now what's interesting about this kind of wave is that even though we don't often think about longitudinal waves, these are the one we most often interact with. And this is why. A longitudinal wave is also called a pressure wave or a sound wave. So sound waves are actually, in fact, longitudinal waves. We might as well add in some more terminology while we're at it. The regions of increased pressure or density, well, they're called compressions, and the regions of decreased pressure and density are called rarefactions. So we can, if we think of our air particles, if our sound's moving through air, we can look at it as our wave looks something like the diagram below, with areas of high concentration of atoms and areas of low concentration of atoms. And no great shock, a transverse wave is a wave in which the particles of the medium move in a direction perpendicular to the direction of propagation. So it's funny because these are the ones we most often think about when we think about waves, and sound waves aren't transverse waves. We often will draw sound waves and make them look like transverse waves, but it's a misrepresentation. It's just because it's easier to draw them that way. So we need to keep in mind that sound waves don't look like, if we can use the word look, don't look like what we normally draw them as. So how can we reconcile those two models? Well, if we, instead of looking at the pressure wave in the way we were looking at it previously, if we instead look at a plot of pressure versus time, well then we can translate those compressions and rarefactions, take our compression and make it high concentration or high pressure, and our rarefactions as low pressure. Then we wind up with sort of this traditional kind of sine wave. And we've now reconciled our sound wave with our traditional view of what a wave looks like. And now that we've got that kind of picture, we should walk our way through the anatomy of a wave. So this will give us some terms that we can use when we're discussing waves. So the dashed line on this picture is the equilibrium position of the particles. It's the sort of center line, if we want, for our wave. And once we have that center line, we can talk about the movement of the wave in relation to that equilibrium point. So when we have maximum displacement, we can call it crests. And when we have minimum displacement, we can call it a trough. And if we measure from the equilibrium point to the maximum displacement, we can call that the amplitude of the wave. And it's worth noting that the higher the amplitude, the more energy we have associated with the wave. A few more little descriptors. If we take the distance between one crest and the next crest, or, of course, one trough and the next trough, or in fact any consistent position of the wave, we can call that the wavelength, and we can represent that by lambda. And our sort of default units then would be meters. But a wave, of course, propagates through time. So if we can measure the time it takes for a complete wavelength to pass a given point. So if we take point F, for example, and we wait for another maximum amplitude, that's a full wavelength. Well, we can call that the period of the wave, and we can represent that by capital T. And of course, since it's time, it has units of seconds. And then we can do a quick calculation. We can say that the time required for a given number of cycles is our period, and measure that in seconds. However, we often describe, rather than describing the period of a wave, we'll talk about the frequency. And the frequency is just the inverse of the period. So if we move backwards, we can say it's the number of cycles per time. And frequency is very useful, so it has its own name for its units. It's 1/seconds, of course, but we also refer to that as hertz. Now with these things in hand, we can calculate the speed of a wave. Of course, speed is change in distance with change in time, but we know that the distance, a wavelength, is covered in one period. And of course, if we substitute in the frequency for 1/period, we can see that the speed of a wave is lambda times the frequency. And we might as well try out a few problems using this. So it's been measured that the speed of a sound wave in air at room temperature is 344 meters per second. Once we have that, if we know the frequency, for example using a tuning fork, we can then calculate the wavelength using the velocity and the frequency. And we've done so here. So the wavelength is 344 meters per second divided by 125 inverse seconds gives us 2.75 meters. Okay, so there's our quick introduction to waves. We'll do in class a Slinky activity. I'd encourage you at home to read the textbook chapters and then do the conceptual questions that are listed on the screen. Thanks very much for your time. Have a great night.